Okay, great. Thanks. So last time we ran into a little bit of confusion with the skolemization of a formula. So remember, this was kind of a trick for turning formulas that have existential statements inside them into formulas that don't have any existential quantifiers inside them, but we do introduce function symbols in place of them. And we do this in such a way that we still get equivalence, provability, equivalence of models, and everything like that. That's the aim of what the skolemization is trying to do. What I introduced last time was this big, long-winded definition for how, if you give me an arbitrary first-order formula, I can take the skolemization of that. And if you remember more precisely, I was saying that you can take the ith skolemization for that for any I equal to any number less than or equal to the total number of existential quantifiers that you have inside your formula.
Okay, that was bad form.
And where the confusion arose was what happens if I try to take the skolemization of a formula that has an existential quantifier that's inside a negation. So maybe I just had some completely random statement like this, right? Then the important point is that this existential quantifier, it's kind of not a real existential quantifier, right? Because if I were to put this into some kind of standard normal form, so if I were to put this formula into a normal form by pulling all of the quantifiers out the front as far as I can, then that existential quantifier is going to turn into a universal quantifier, right? So you kind of have this question, what are the existential quantifiers? This one that I've underlined in red, is that an existential quantifier or is it a universal quantifier in disguise, right? Okay, so that was a very good observation that Billy made. And my counter was that it doesn't matter. And the reason why is because the skolemization, for the sake of the proof that I'm giving of the X growth index theorem, the skolemization could just go ahead and give something completely meaningless inside these examples. So the definition that I gave still holds. You can just decide that that is an existential quantifier and you can replace it with a Skolem function symbol. You just might not end up with any formula that has any relationship to the previous one whatsoever, right? So that's a bit clumsy and that's a bit messy. The way that we can make this a whole lot clearer is to introduce what's called the Prenex normal form of a first order statement. And this is what the missing piece was last time. The Prenex normal form is a negation normal form, and it has all of the quantifiers pulled out the front. So let's define such a thing. A first order formula phi in some first order theory T is in Prenex normal form if phi is equal to quantifier 1 x1 ... quantifier n xn phi prime with phi prime quantifier free. Right, so Qi is an element of for all, and there exists here. Okay, and then as long as we only ever consider formulas that are inside Prenex normal form, then this question doesn't arise. So to put it explicitly, this second first order formula that I wrote down is not in Prenex normal form. So you get this kind of confusion as to what the quantifiers really mean, but the first one is in Prenex normal form, so it's very explicit. These are the existential quantifiers that I wish to replace, and in such a situation, I do get equivalence between the original first order formula and the Skolemization of the formula. Okay, and the proposition which I'm going to use is that every first order formula has an associated Prenex normal form, which is equivalent in quite a strong sense. So you can prove the Skolemization you can prove the Prenex normal form associated to a first order theory from, associated to a first order formula from the theory that formula is defined over and that first order formula that you started off with, and then vice versa. So I can write down that proposition, and for this seminar we will be just taking this for granted. Proposition. For every first order formula phi in some first order theory 2, T, there exists Prenex normal form phi such that T union phi can prove var phi or phi, and T union phi can prove phi. Cool. Okay, and then in his first order theories, where all of the formulas are in Prenex normal form, which we're going to be concerning ourselves with. Okay, so now let's try to head towards the lower Lowenheim-Skolem theorem. The lower Lowenheim-Skolem theorem is a statement that if you have a model for some first order theory, then if that model is an infinite cardinality, then you can also construct a model of the same first order theory, but of any cardinality less than the cardinality of the original model. There are a couple of more hypotheses that you need, but these are just hypotheses upon the first order formula that make the Skolemization satisfy this proposition, right? So I'm just going to be assuming that we are dealing with first order theories where all of the formulas are in Prenex normal form. Okay, so that's the goal. We'll start with the lemma, which relates a first order theory to its Skolemization. Okay, I'm assuming that T is over a language with only one sort. Okay, and I'm assuming that all of the formulas are in Prenex normal form and closed. By closed, I just mean that the formulas have no free variables. So the free variable set is the empty set. And the statement is, if T admits a model, then so does the Skolemization. Oops. Then so does the Skolemization of T. Okay. Now, let me prove this. Okay, I'm going to need to talk about the number of variables inside phi which are bound specifically by an existential quantifier. So I'll let this integer be denoted m. Okay, and the technique, it's a proof by induction of sorts, but I'm inducting on a finite quantity. So really what I'm showing is for any I equals 1 up to m minus 1, if there is a model a model I such that the interpretation of the ith skolemization is equal to 1, then there is also a model of the I plus 1th skolemization.
Sorry, what is the formula phi from? Is it just any formula at all, or is it like one
This
that's
is
true in the...
this is one of the formulas that are inside the first order theory T that satisfies the hypotheses inside the lemma. So I thought that I put phi in the statement. Did I not do that?
Yeah, you did. I was just checking.
Okay, cool.
So you're doing, you're proving something about each phi.
Yeah. Okay, and this is the statement that I'm proving, that if I have this interpretation that interprets the ith skolemization as 1, then what I'm going to do is I'm going to extend I to an interpretation that interprets the I plus 1th Skolem function in such a way where the interpretation is definitely equal to 1 of the I plus 1th skolemization. Okay.
Uh-huh. Is there a reason that it's so called I?
The interpretation or the index?
The interpretation you said also called I in brackets.
Because I'm extending I, so I is an interpretation, and what that means is that we have an assignment of a function to every function symbol, we have an assignment of a relation to every relation symbol, etc. And all that I'm going to end up doing is extending I to also interpret the I plus 1th Skolem function, which does not appear inside S of phi I, right? So I'm just lazily calling it I because it's an extension. In reality, call that J, and then identify, just observe.
Yeah.
You can observe afterwards that I is an extension of J. Okay, so all I'm going to do is take the leftmost existential quantifier and replace that with a Skolem function and observe how the interpretation flows through that substitution. It's actually a pretty simple proof once you look at it. So let Y denote leftmost existentially bound quantifier in phi, and let x1 up to xn be those variables inside phi that are bound by universal quantifiers that occur to the left of y.
Do you mean an existential quantifier in phi or in S phi I?
Oh, that's a good question. I do mean S phi I. Thank you. Did I get that wrong in the notes? Yep. Okay, good pickup. Thanks. Oh, yeah, that flows through. Okay, that's fine. We can adapt. So S phi I, keep in mind phi is in Prenex normal form. So all of the quantifiers are at the front. So S phi I we can write out pretty easily. It's a whole stack of universal quantifiers, and we know that there's n of them by definition of n. And then there is the existential quantifier, y, followed by phi prime, and we just have no assumption on phi prime, right? So phi prime may or may not have quantifiers. Okay, but that's helpful because now I can relate the I and the I plus 1th Skolemization. We notice that the I plus 1th Skolemization is equal to S of the formula for all x1 dot 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 for all xn there exists y phi prime. I haven't done anything complicated in that step whatsoever. That's just the previous line. And that's I plus 1. And then that's equal to the ith Skolemization of phi prime, but I'm going to do the substitution of y for the I plus 1th Skolem function manually. So I just put here y substituted f I plus 1 of x1 up to xn, square bracket, comma, I, close bracket. Right? Okay. And then I'm going to use the fact that I have a model of this in order to define a function, which I'm going to interpret the I plus 1 function symbol as. Okay, so I need to move to the next board. And do we do platforming for that? I think we do.
You can also walk around. There's another way up here.
It's more fun.
Everyone finds their own way.
I got 2 characters to do, so give me a second. Oh my god, I went the wrong way.
It's better to walk on the vents. If you jump on them, you don't go as high.
Really? I'm having the opposite experience right now. Okay, there we go. We already established that I have no humility, Dan. Okay. Okay.
We've got halos in the orb cam. All good now.
I don't have a halo. That doesn't pertain to me. Okay. So we'll define F. I guess I should say what A is. So A is just going to be the one and only sort inside our language. So and then I'm going to go ahead and define this. Okay, So what I do is I say, let mu be some valuation, and we know that I sub mu of S phi I is equal to 1. And so this means that, I won't use full quantifier. That means that for all tuples of elements inside I of A to the n, there exists E in I of A such that I, with the adapted valuation of wait, how did I need to look at the previous board, which is downstairs now. So I just need to check the error in the notes is flowing through correctly. So
You can
S,
zoom out.
oh yeah,
See it.
good thinking. That's okay, let's just write this. So recall that S of phi I is for all x1 for all xn. Yeah, and then that's the ith Skolemization. So we have exists y phi prime. Okay, so this sentence here holds. What do I need?
Sorry, what's E?
Oh, these are the E's. So for,
but wait, you said for all of those there exists E.
yeah. So I haven't finished the. Oh yeah, I did leave it out. So I haven't accounted for the E is going to be some element where if I interpret Y as that element, then I get the evaluation mapping to 1, right? We know that such a thing exists because we have a model of the Lowenheim-Skolem.
Right. So you're not saying that E's not the tuple E1 up to En.
No, sorry. It'll make more sense once I've written my thing, right? So don't forget that the Skolemization was this thing, and we know that we have a model for that. And so for every E1 up to En, if I do these substitutions, there exists some some E. Essentially, if Y gets interpreted as E, then this entire thing maps to 1, right? And so this is the point, this is the exact point in the proof. This comment's mainly for Billy, where last time you were asking if this entire thing is equivalent to choice in some way, right? Because we remark at this point that there's not necessarily a unique E, right? So what I need to do is making choice of E for all such tuples. I'm doing that in the meta theory, right? So Dan, you also made a comment about this last time. So I'm using choice in the meta theory here. Choose an E for all such E1 up to En. And then I'm going to define F from I of An to I of A as E1 ... En maps to that E. And then I define the interpretation of Fi plus 1 as this F, right? And then I've clearly extended the model out to the I plus 1 Skolemization, the first order theory pertaining to that. So that's an interesting step. Does anybody have any comments about that? Yeah, I mean, I feel that. Can you put that into words though?
Into big words.
Do you want me to say it again? You see, we don't know that this E is unique, but we know that it exists because of this. We know that we have some interpretation that sets this equal to 1. Now, what that interpretation says is that when you get to this existential quantifier, there has to be some element inside the domain. Essentially, if I set y to be equal to that element, and then I carry on with my interpretation, I eventually get down to the value 1, right? Now, the interpretation doesn't have an element E in its hands, but I, as a meta theory, am saying there is such an E out there somewhere. Make a choice of such an E for each tuple E1 up to En, and then use that to define a function, right? So the interesting question is, what have I used in the meta theory to do that? And I believe the statement is like, it might even be strong choice, right? So I've got some pretty heavy hammers inside the meta theory at this point.
Where are you, Will? It seems like there's a wind in your microphone or something.
Oh, damn it. Yeah, you caught me. I'm outside. Do I need to... Is it really bad? Or is it okay?
Just now it was. It's sort of
Just now it
noticeable
was.
in general, but it's not so bad. But just then it was pretty severe.
Okay. I don't have a good place at the uni to make a lot of noise. Okay, do tell me if it gets really bad, and I'll jump inside. I think I can see a spot, but I'll try to persevere with this for now.
Sure. Yeah, I don't have any sensible grounds for complaint about the choice business. I'll just stew on it quietly.
Yeah.
I thought you were a fan of choice.
I'm a fan of choice when it's an axiom, not some voodoo that happens in the meta theory.
Yeah.
But okay.
Yeah. I agree with Dan.
An axiom of the meta theory. We're just doing normal mathematics
here. It's totals all the way down. That's what I just heard.
Yeah. The one thing that I would continue on, Dan, though, is when we were doing the lecture on models, I was talking about all this hoo-ha of the Platonistic existence of objects and math out there, etc. And you kind of refuted that by saying all that you're doing with these models is reinterpreting first-order theories in other first-order theories. So my understanding is you're essentially just taking everything that happens inside a model is happening inside the first-order theory of ZF or ZFC or ZFCU, whichever one you kind of pick to take, right? So if you just go ahead and take ZFC, then I've just used the axiom choice inside ZFC there.
Yeah, I'm totally fine with that. If this is all like inside some theory, then fine, you get to use choice in the meta theory, which is just ZFC. That's of course fine, but you're going to proceed to talk about it in a way where you aren't thinking about it exactly like that, I think.
Yeah.
Anyway, this is kind of not something we should get derailed on again, I think.
Sure.
Billy, your halo is too shiny. Move.
Oh, right.
Okay.
I think you're making too many assumptions about where we're going to go with this.
Okay, I will lurk in my den and wait for you to make a mistake, and then I'll rush out.
I think this is just normal mathematics, and the things that we do here you hold to much higher standards of what it's supposed to magically achieve than like regular mathematics that we do in other seminars.
My impression so far is that we're using a lot of symbols to say something that is kind of obvious.
The idea, Eleanor, is to pin on what you consider obvious. So we're trying to challenge, you're saying that picking a representative of these E's for every tuple is obvious. Now that's what you've said there, right? And you can go ahead and hold that opinion, but let's be aware that that's what you're saying. And then when you chase that, it gets pretty weird. I was going to say, I had a point that I wanted to pin down on, but I forgot. That's a shame. Okay. I'm going to skip the proof of this lemma. It's basically identical to what I just did. It's just in the opposite direction, right? So this essentially says that if I have a model for the Skolemization, then I have a model for the original one. But you need to get your assumptions correct. So if I have a I need to have a model of the skolemization that evaluates to 1 in this particular, for this particular choice of formula. So this is for all phi inside some first order theory T, and then I'm just going to lazily write same hypotheses as previous lemma. Okay, so it's essentially a converse. And you can just,
direction should be like a whole lot less controversial because we're starting with all the choices and then we're just removing them and just reducing them to an existential.
Yeah, exactly. Okay, lower Lowenheim-Skolem theorem, the moment we have all been waiting for. Okay, I'm going to write out all of the assumptions that I've been making just to get a very precise statement. T is a first order theory with only one sort, and all the formulas are closed and in Prenex normal form. Okay. Are you ready? Are you ready for the hypotheses? So this is going to be a whole bunch of cardinality stuff. Assume the language T is over has at most countably many function symbols. Is that it? Yeah. Assume that we have a model. There is a model I of T with the magnitude. So this is the cardinality. The cardinality of I of A is infinite. So some infinite cardinality. Okay, and then for any cardinal kappa less than or equal to the magnitude of I of A, so less than or equal to the cardinality of I of A, there exists a model J of T with the cardinality of J of A is equal to kappa. Okay, so there's an upper Lowenheim-Skolem theorem as well, which gives us the general Lowenheim-Skolem theorem. But you can see why this is the lower one, right? We're just saying that if we have an infinite model, then we can get all of the cardinalities less than that model under certain hypotheses. So there are more general statements than this. So asking that we have at most countably many function symbols is just to make the statement and the proof a lot easier, but you can remove that hypothesis and get a weaker statement. It's not necessarily equal to kappa, but it's equal to the maximum of kappa or the cardinality of the set of function symbols that you have. And there's nothing inside this theorem that requires you to only have one sort as well. That's just a simplifying mechanism because that's all that we need for the Axe-Grothendieck theorem. Cool. Is the statement clear? Okay.
Yes.
Nice. Proof. Okay, so let me tell you what we're going to do. It's it's just a sneaky sleight of hand. I'm going to grab an arbitrary subset of I of A, which is of cardinality kappa, and then I'm going to take the union of that thing along with the image of all of the interpretations of the function symbols of the language. Now, since I've only got at most countably infinitely many function symbols, the union of the subset of cardinality kappa and all of those images is kappa, right? But if I think about that model, it has the images of all of the function symbols inside it. And so I can definitely create a model inside that. I'm basically just restricting the model down to the minimum that I need, which are the images of the function symbols, and then I extend it arbitrarily out to some set of size kappa, and then we're done. Okay. Did I not say that?
No, you didn't. I was also wondering this.
So in the statement, did I not say it? Let me have a look.
You didn't, yeah.
Okay. Yeah, that's important. Oh, for any cardinal. Yeah, that's not right. For any infinite cardinal. Okay, good pickup. Thanks. Let D, subset of R of A, be an arbitrary subset of cardinality kappa. Okay. And now, yeah, I'm going to consider the Skolemization of the first order theory. And the reason why is because the interpretation might end up picking an element that of I of A, which lies outside the images of the interpretations of the function symbols of T when I have to interpret an existential quantifier. So if I remove all of the existential quantifiers first, then I can control the codomain using the function symbols. That's the whole reason why we needed the Skolemization, by the way. So that's the crucial point in the proof where Skolemization is used. Okay, and then we've already we proved earlier that since we have a model of T, we have a model of the Skolemization of T. Cool. Okay, now let's look at all of the function symbols inside the Skolemization of T. This is going to include all of the Skolem functions. So to each of these, I consider the image of the interpretation. So I take image of the interpretation of F, restrict it down to D, right? Because I can just go ahead and restrict the domain of the valuations to D, and then I do the same for my function symbols, and we still end up with an interpretation. Okay, so pick an arbitrary valuation, new. And now the set that I define, and this is going to be the domain of my kappa in cardinality model is E, which is the set D, and then I union the image of nu, and I union the big union of all, taking the union over all of the function symbols of the image of I of f restricted to D. Okay. Now, this is the most important step in the proof. This definition, along with the observation that it works. So the first thing that you need to make sure of is that you have indeed ended up with something that is well defined. Taking all of these images is what is needed, because we're taking functions out of the set D because they're all restricted down to D, but I need to make sure that I end up with elements inside my domain, and so I just union all of the images to guarantee that. Okay, and then we need to make sure that this has the correct cardinality, and the observation is that this has cardinality less than or equal to Aleph null, right? Because there were at most countably infinitely many function symbols. The image of the valuation, well, if you go all the way back to when we defined first order theories and first order languages, we said that there is a countably infinite set of variables associated to each sort. And so therefore the image of this set has cardinality also less than or equal to Aleph null. Okay? And then D is the arbitrary subset of cardinality kappa that we took right at the very start. So this has cardinality equal to kappa. Okay? Kappa is at least infinite. So therefore, the cardinality of E is equal to kappa. Does that make sense? So, as I said, that's the most important part of the proof. And then the rest is just to check that this indeed works. So let's go up a layer.
Wait, I actually had a question.
Yep.
So the first one is, if we started with only finitely many function symbols and variables, like, of course, that's like, you don't want to have finitely many variables, but just for the purpose of this theorem, could we drop the infinite cardinal assumption on kappa?
That's a good question.
Seems like that would make all this still work, right?
I think that kappa would have to be a cardinal greater than or equal to the maximum of the cardinality of your variable set, or the cardinality of your function symbol set, and then I think it works.
Right, yeah.
You need the cardinality of D to be... Oh, wait, there might be more to it than that. Because the cardinality of this union is now going to be additive, right? So...
Yeah.
I think
I guess you
to make... Sorry, you
take
go.
small finite sets and make like
Yeah.
Okay.
Yeah.
And
if you did that, by the way, that would be insufficient for the Axe-Grothendieck theorem, okay? Because the first order theory of algebraically closed fields of characteristic 0 had infinitely many formulas, and so you've got infinitely many Skolem functions. So you have infinitely many function symbols.
Right. The other one was, so the Lowenheim-Skolem theorem is clearly about the existential quantifiers, and makes sense to me how to use this Skolemization.
Yeah.
there's the sort of presence of existential quantifiers make the size of the set of objects get bigger. But for universal quantifiers, like, we don't really care because we're making the set of things smaller. So like a universal
Exactly.
quantifier was true earlier is like remain true. In the upper Lowenheim-Skolem theorem, do you have to like concern yourself with the universal quantifiers in a dual way, or?
Yes, that's a really good question. You don't, because there's a slick trick that happens when you get to the upper
Like with
upper
negation or
Lowenheim-Skolem
something?
theorem. I like your thinking. Look, probably both techniques will work, right? But what we're going to do is just introduce a set of cardinality kappa worth of constants, right? And then I just add all of these formulas to the theory that say every pair of these constants are not equal to each other. And then I use see, it's like symbology. And then what I do is I use the fact that we have the compactness theorem. So since I have all finite models of that, because I can always just pick for any n elements of my infinite cardinality model and get distinct elements, and all of the formulas are provable and hold inside that model. I can do that for all finite subsets, and so therefore I get some infinite cardinality, which is at least greater than or equal to kappa, because we have to accommodate for all of the constants. And then I appeal to the Lowenheim-Skolem theorem to shrink the possibly too big thing back down to exactly kappa.
Right.
Yeah.
Cool.
So that's the trick that will be used there.
Let's keep going.
Tell me again how logic is a dignified discipline. No offense.
Dan, if you want to be invited to future lectures, no offense, okay? You can learn to be a little bit more polite. Okay?
You jump off the wall.
Yes, sir.
Yeah. Look, like I don't want to encourage your rudeness, but I see your point. I find it surprising that all of this is needed for algorithmic as well, is the thing. So this is where I really got the belief that this surely wasn't how they proved it originally. At least this content wasn't invented by the algorithm. That much certainly is true. But I wonder if you can just specialize everything and get down to a much simpler argument. But yeah, there's a lot of ad hoc stuff inside first order logic. It's part of my complaint of first order logic. I would expect the world's most natural logical system to not have so many ad hoc movements. Like even the Prenex normal form, like, come on, really? I can't believe that I have to do all of that. But these are questions to be explored.
I guess I'm willing to believe that this ad hoc stuff is not really significant, and I'm just not seeing the ideas clearly. And that's no criticism of you, but it does. I'm just communicating the feeling I have listening to this is kind of like, okay. Doesn't. I'm not seeing the deep thing happening in front of me, which is okay. But
I have a lot of the same feeling. So the common slogan for the Lowenheim-Skolem theorem is that first order logic can't internally tell the difference between cardinalities, right? So maybe that's what the shortcoming of it is. It's like you have some finite system, and so you can indirectly talk about higher cardinalities, and maybe you could interact with computably, countably infinite sets.
Okay, I take it back.
We as humans can never do
that. That sentence you just said made okay. Now this childish-looking operation you just described has a clear conceptual content for me. So I withdraw my tantrum throwing. Your head is in the way of the board though. Before you start writing on it in the orb cam.
My head, yeah, okay. All right. Thanks. Okay, I really want to finish this proof. So So, I mean, we're basically done, right? So we define the model J. J of A is going to be a set E, which I've just defined. And then for all the function symbols, I define J of F to be the function that I interpreted F with using I, but I just restricted down to D, D to the L, right? Where L is the arity of F. And then the relation symbols, they don't map back into E. Keep in mind that relation symbols are interpreted as predicates. They map into either 0 or 1. So I don't need to do anything to the relation symbols except restrict their domain. Cool. And now we're done, right? So the observation is that everything gets interpreted in exactly the same way. I've just cut away a whole portion of the set I of A, which is not visible to any particular element of this interpretation. So no domain of any interpretation of the function symbols, no codomain, no domain of the relation symbols ever see those extra elements. So if I were to just do the interpretations, everything's interpreted exactly in the same way. And so obviously J of phi. So the observation is that J of S of phi is equal to I of S of phi is equal to 1 for all phi in T. And then by the lemma that I didn't prove, this implies J of phi is equal to 1 for all phi in elements of T. Okay.
Wait, you use the direction
I used both directions inside this proof. I used the first one viewports back, and in this one, I just used the one that I didn't prove. Make sense?
Yeah.
Okay, good. Okay, cool. So that's the lower Lowenheim-Skolem theorem. There is, I'm concluding now. There is also an upper Lowenheim-Skolem. That's going to be next time. And just to let you all feel like the light at the end of the tunnel is starting to appear, this is all going to imply the, I can't pronounce this guy's name, the Wash, W? Okay, Wash Fort test, which determines completeness of a theory. Okay, and then I just make the observation that the first order theories of algebraically closed fields of characteristic P and also algebraically closed fields of zero characteristic satisfy the hypotheses of the Wash-Vort test, and so therefore those are complete theories. And that was all that I needed to finish the proof. We've already completed the proof of X growth in data under that hypothesis, and so once we have this, we have that hypothesis, and then we're done. So I should be able to finish next time. Okay, thanks and questions.
Yay, thanks guys.
Welcome.
What you were saying about the upper Lowenheim-Skolem theorem, about how like you start with your theory, or I guess this applies to the lower one, where you sort of change the theory and then you get this other theory that or this other model that kind of ruins your day, because trying very hard with versatile logic to sort of pin down a cardinality. It sort of reminded me of like a little bit of like the halting problem for Turing machines. Like when you're trying to, in a particular domain, like you have a you have a problem that's equivalent to solving the halting problem, but you think you can solve it by like trying to detect all these little cases, and then that like there's always just one like sneaky case that sort of evades everything that you've attempted so far. Yeah, it kind of reminded me of this, I guess. Like
I had
my
more of those
reaction.
feelings with the first incompleteness theorem than here,
Mm,
because that's
more
the point.
specifically,
You go.
my reaction to like the like when I first saw the proof of that like there's no Turing machine that decides whether a Turing machine will halt. It's it was like, oh, why can't you just? Well, I don't really care that like it doesn't
Mm,
work when you run it on itself or something. Like, what
mm,
if I could just decide if all the normal, sensible Turing machines halt and not just this like
mm,
pathological counterexample Turing machine that like ruins
mm.
the the fullness of its ability to detect halting. So like in that way, I guess I'm I'm sort of addressing the idea that like these modifications of the theory, like like this one where you chuck in all these extra constants and say they're all not equal. Like we obviously do not care about that
Mm,
particular theory for any practical purposes, but it's like, but it's just the sort of pathological thing that can happen within the realm of what we say can count in first order logic as a theory that
mhm.
that sort of is the reason why first order logic can't distinguish cardinalities very well.
Interesting. So the way that I think about that trick that we're going to use is that there is a clear relationship between the original model and that one in terms of there's kind of this injection. Like if you take your first order theory and you just add a bunch of constants that you don't really care about, and then you extend your model to care about those constants, but that extra model is basically a disjoint union. There's the original model, disjoint union, another set out there that just handles these extra constants, right? Then the point is there's no barrier to injecting some lower cardinality model into a higher one, right? So if I can prove something to be true inside some lower cardinal model, then I can just increase that set, and I don't now lose truthhood of that statement, right? So it's like non-pathological almost, because that would be weird if I could add stuff that we don't care about and all of a sudden the statement becomes false, right? Anyway, and the reason why that's interesting is because if I have a statement that is provable and also its negation is provable inside the same cardinality model, then I can do a bijection argument and carry truth through that bijection, which is going to give us a contradiction, which is going to prove the Wash-Vaught test. So the point is that all I'm really saying is I've got these two models. One's bigger than the other. Who cares? Like one's an extension of the other, right? And the formula is true in one of them and it's false in the other one. And the point is that is a contradiction. You might say, oh, how do you know? Like those models are of different cardinalities. You need to set up some map from one into the other and check. It's like you kind of roll your eyes and you're like, yeah, sure, fine. But then you do that and it does work. So I think it's more about relating extensions and restrictions of models, and we use the language of cardinality to describe it because we use bijections in order to carry truth between models. That's really what's happening. Yeah. So there is tons of redundancy. I would be very interested in some modification to first order logic where these redundancies don't appear. I feel like that would be a more natural and close to the machine logical system.
What do you
But I don't
mean
have-
specifically dependencies?
I think there's a lot of them. I think that the fact that you can write first order formulas not in again distracted by the nature.
Another giant tree.
Yeah, the giant tree walking around. The fact that you can write formulas not in Prenex normal form, for example, is what I mean by redundancy. Like, why do we have formulas that aren't in Prenex normal form? You know?
Yeah, I don't really get your point there. Could you speak more to that?
Okay, so let's think about the injection of like natural deduction into proof nets or something. That's where these ideas really come from, in my opinion. Proof nets are very
See ya.
Did you just yeet Will into
Whoops. Okay, that was bad form. I was planning to stand on his head and then let go of the tree, so he possessed it unwillingly. That was my aim. Where did he end up?
I don't know. He should come down at some point. Yeah, we can't hear you. Oh my god.
Oops.
How could you?
Yeah, that's pretty bad.
He was mid-sentence too.
Oh well, he'll come back enlightened by his journey through the cosmic spaces.
He might have yeeted so high into the air that he actually exceeded the like boundary from above. Like there's a boundary at which it just starts destroying parts.
Well, he didn't reset. He quit.
I am gonna go now. You'll have a good night.
Okay.
See ya.
See you, Anna. Thanks for coming. Yeah. Well, I was expecting him to fall back down at least. I don't know what happened. Okie donkey. Well.
Might as well do something productive and eat his other. Oh, what?
Oh no.
What?
What was that? He just sent himself. Can you hear me?
Yeah, that was interesting.
Okay, can you hear me?
Yeah, I can hear you. Did you see what happened to Dan just then? What did you do?
No, what happened?
I went flying up where you were.
Well, he like.
Yeah, I got completely piffed. It was really quite funny.
Did you go like so high in the sky it like killed you?
I have no idea where I went, but I was rotating at an incredible rate, and I was in the middle of nowhere. I didn't die, but I was definitely launched.
Oh, so you didn't kill you, but you just quit before it.
Yeah. Okay. Let me finish my sentence. Now, this is something that I haven't fully made up my mind about, but I think that there's an interesting observation to be made. Proof nets are kind of interesting because they move away a lot of the different ways that you can write what is quote unquote the same proof, right? And this is a common complaint over systems, for example, the intuitionistic secant calculus. You've got all of these different commutation rules that need to be modded out before you get the same lambda term inside the Genselman's-Zucker duality, for example. So the same quote-unquote proof is written out in a billion different ways, but proof nets only have one way to write out the same proof, if you distinguish cut equivalence. And what's interesting about that is it reveals mathematical structure. For example, the sequentialization theorem or the cut elimination theorem, I suppose. But let's go with the sequentialization theorem. That also holds for intuitionistic proofs in some sense, but it's much more difficult to observe and to see because your notation is cumbersome. You've got redundancy inside your notation. Okay. Now, sometimes that redundancy is in fact a positive thing, though. For example, in the lambda calculus, you also have that redundancy if you distinguish alpha equivalent terms. So you've got all of these different ways of writing out quote unquote the same term, right? But that's kind of in fact beneficial if you because the reason why it's beneficial is because people have defined lambda calculus systems where the alpha equivalence is not visible inside the notation, and it comes down to really awful things like bracket counting and stuff like that. So a computer would be able to distinguish the terms very easily, but a human would struggle to. And so the alpha equivalence, in fact, makes it easier to read, even though it's redundant. But that makes sense anyway. Redundancy increases simplicity of reading it. There are many different ways to read the same thing. Okay, but this fact about the proof nets being eloquent in that they only give you one way to write out the same proof is really interesting to me, because I think that when you have less redundancy in notation, you have a higher chance of revealing mathematical structure. So I think that first order logic is very interesting because it seems to be very close to the way that we as humans ever could possibly reason. But when you do anything with the system, you realize that there's a lot of redundancy and a lot of tedium involved in working with it. So I wonder if there's a more elegant system that does away with all of that redundancy, which might reveal more mathematical structure, for instance.
Yeah, I mean, you're skating close to topics that are related to statistical learning. There are key advantages to redundancy that come from, well, exactly the things you're talking about. You can make some of that formal. So I would speculate that there's a limit to how much redundancy you can eliminate without making it very difficult for finite learning systems to actually find those terms or proofs.
So interesting. Yeah, you can literally see that with the lambda calculus. Like, go and have a look at these notations for the lambda calculus that don't have alpha equivalents inside them. And that's literally the problem that you run into.
Yeah.
So it doesn't surprise me. That's really interesting. I might look into that.
Billy, can you stand just here? No, don't move.
You're gonna jump on.
Did you do it?
He's a goner.
Yeah, it looks like it. Is that how you get rid of the student that keeps asking questions?
Yeah, this is a great technology. This is called innovation in teaching and learning.
Yeah, I think that we need a real life one for in the flesh lectures.
Yeah.
Well, I guess they call those things catapults.
I'm going to leave before he comes back because he'll be angry. So thanks, Will.
All right. Yeah, no sweat. And thanks for staying up again. I'll see you next time.